We have a bipartite graph with two sets of vertices, set U, which contains element U1, U2, U3, U4, and set V, which contains element V1, V2, V3, and V4. And we have a matching M, which includes the edges U1, V1, and U2, V2. And we have another matching M star, which includes the edges U2, V3, and U3, V2, and U4, V4. And we have a set which contains edges that are in the symmetric difference of M and M star. The symmetric difference is the set of edges that are in either M or M star, but are not in both. So in this case, the symmetric difference would result in the edges U1, V1, U2, V2, and U2, V3, and U3, V2, and U4, V4. In our diagram, there's no cycles, and the symmetric difference creates a simple path from V3 to U2 to V2 to U3 and an isolated edge, which is U4, V4, and U1, V1. This could represent the case where the cardinality of M star is equal to the cardinality of M plus 1, which suggesting the existence of M-augmenting paths, which could potentially increase the size of matching M in the graph G if M star is greater than M. In the graph G prime, with edge set E prime, which is the symmetric difference of M and M star, has a degree of either 0, 1, or 2 at each vertex, meaning that each vertex is connected by at most one edge from M and at most one edge from M star. So each connected component of G prime is either a singleton vertex, an even-length simple cycle with edges alternating in M and M star, or a simple path with edges alternating in M and M star. If the cardinality of M star is greater than the cardinality of M, then E prime must contain the cardinality of M star minus the cardinality of M more edges from M star than from M, and each cycle in G prime would have an equal number of edges from M and M star, and the simple path in G prime would account for the cardinality of M star minus the cardinality of M edges from M star, and each of these paths would be M-augmenting path, and because each vertex in G prime is incident with at most two edges from E prime, and this path would be vertex disjoint.